Hello, KubeCon. I'm Artur Souza.
This is Chunpeng.
Are we ready to handle Black Friday traffic? That's a question that we have to answer every year at Amazon.com, as you can imagine, ahead of the holiday season. And it's not only Black Friday. As you can imagine, there are other holidays, sport events, sale events, and any kind of external factor that can impact the shopping behavior. You might imagine, well, I'm just going to set up reactive scaling and I'm good to go. Not really. So we do use reactive scaling, but for those peak events, it's not enough. And proactive scaling is needed. And me and Chunpeng, we're going to walk you through how we do this at Amazon.com. So let's begin with the user journey. Different services are activated by different business demands. For example, when you're looking for a product, you're of course going to activate search and the product detail page services. When you add an item to the shopping cart, it will trigger the shopping cart and other checkout related services. Once payment is processed, it takes care of the payment through the payment providers, activate those services, and same thing happens for shipping and delivery. It's important to understand the cascade effect of each one of those actions. As you can see, those activate different services at different magnitudes. A call to one service can result in calls to 3 different services, or 4, or a multitude of calls to the same service. This complexity also shows why reactive scaling is difficult to work in these scenarios, because even if one service can react fast enough, it takes a while until the cascade effect takes care of the entire network of services. Let me go through. Let's understand peak traffic a little bit. In this hypothetical example, we have Black Friday and Cyber Monday days. And again, this is a hypothetical example. There is a spike at the beginning. Maybe you just finish your Thanksgiving dinner. Hopefully you brush your teeth before you go shopping. But then everybody goes shopping at the beginning. Then people go to sleep. And then throughout the day, more shop activity happens. We can use this example to explain the user journey throughout the day. It also shows that we must understand the shape of the curve, the rate of change, and the sustained duration of the peak hours. It's not just understanding the whole load, the entire load. Let's look at this again. Look how steep that initial spike is. That is exactly where reactive scaling will fall short. By the time your monitoring systems detect high CPU utilization, triggers the scaling actions, you're already behind the curve, and a significant portion of your customers are already impacted and could not shop for their Black Friday deals. This shows a fundamental change, understanding the peak time, and then importantly, make sure the capacity is reserved ahead. Even if you, for some reason, can scale that fast, are you sure all the capacity is available for you in your cloud provider? The limits are going to be reached. So this leads us to a critical insight. These events have a large peak to mean spreads. This means we need to proactively model the expected peak load and continuously assess our AWS capacity needs to support it. Don't get me wrong, reactive scale is cheaper, and we want to rely on reactive scaling when possible. But during those events, we need to model ahead. Let me introduce to one key metric that we use for our scaling actions. Mean time to traffic, or MTTT. Let me explain how it works. Imagine that your systems are running hot and your monitoring system detects the need to launch a new instance. Then you spin up a new instance, your application starts. It can be a container, it can be a serverless function, and then the health checks get in place. The service is registered behind the load balancer. Any warm-up procedures take place if you have some kind of caching that you have to load ahead of time. Only after all this is done, your service is ready to take load. And that's the metric that we take to understand how fast we can scale and descale each service at Amazon.com. It also brings some complexities because services have dependencies on other services, databases, and queues and other external resources. So that startup time, as you can imagine, is not zero. The breaking point TPS, that means breaking point transactions per second, or per minute, can be many granularities as you need. It means the maximum transactions per second a single service can handle before violating SLAs. And violating SLAs does not mean the service crashing. You violate SLA way before the service crashes. For example, in this example, we can say add cart SLA or start checkout SLA. What does it mean? It means that the time it takes to add an item to the cart has a limit. That's a business metric. And you cannot go beyond that limit because that will affect the customer journey in the shopping experience. So we want to call out our breaking point exactly at that limit, even if the service doesn't crash, or even if there's no increase in error rate. Of course, if there are error rates, we also call that breaking point at that point. We also have dependency that on the service that needs to be included in this testing. We, of course, use a synthetic load generator. And very important, we also take note of the CPU utilization and the memory utilization observed at breaking point. These are very important metric for us to include in our scaling settings. I'm going to summarize some of the variables that we use in our scaling settings. MTTT, like I said, it tells us how fast your service can scale, descale. The typical reactive scaling that people are used with, which is the maximum CPU threshold for you to trigger reactive scaling. And for peak events, we also have proactive scaling formulas. We include the traffic forecast for business drivers. For example, order rate. How many orders are we getting per minute or per second at any given point on each marketplace? That can be used in our proactive scaling formulas along with the breaking point TPS to convert the forecast into instance count. And service owners can also use other independent variables to compose a richer scaling formula. And all that is calculated way ahead of the event. So you know what capacity you need to be reserved and at what point you need to start scaling. You might be asking, well, I just use serverless. I don't need to do any of that. Not really. Serverless still have an MTTT equivalent, which is the time it takes for it to react to your demand. And as an example of that, you can see how Amazon's DynamoDB start offering in 2024 pre-warming APIs. What does it mean? It means that once you have calculated your capacity needs for a peak event, you can invoke this API and set your DynamoDB tables to be ready to receive a higher traffic than it's actually receiving at the moment. Of course, there is a price for that, but it shows that regardless if we're using containers, VMs, serverless functions, there is always the need for capacity planning for peak events. Now let me hand it over to Dr. Chunpeng Wang, who's going to walk through the forecast logic behind all this at Amazon.
Hi, everyone. As you know, shopping events like Prime Day are huge for Amazon. We receive significant higher traffic than normal days. They drive our peak capacity needs and define infrastructure planning requirements. Think about it. When you visit Amazon website, thousands of services are working together to support your shopping experience. It's not about scaling just one single service. It's about orchestrating the entire ecosystem of interconnected services, each with their unique performance characteristics and bottlenecks. So how do we handle this massive challenge? As Artur mentioned, we cannot fully rely on reactive scaling. We use forecast to set the expectation of the future. So now let me walk you through the process to show how we map uncertainty into actionable capacity plans. Here is what it looks like in practice. The chart shows daily peak traffic using synthetic data. The green line is daily maximum traffic. The purple line is the forecast extending through next year. Note that there are two peak events in a year. That's Prime Day in July and Black Friday in November. The forecast guides everything we do across multiple horizons. On the 1-year horizon, we communicate the long-term capacity projection to AWS so that we can work on data center construction and power infrastructure preparation to support our anticipated growth. 6 months ahead of the event, we place our capacity orders so that AWS has enough lead time to work on data center hardware procurement and rack building. 1 month before the event, we get the capacity we ordered, and we start allocating and work on event readiness. Everything seems ready to go, but is it really that simple? Here is the reality. We could overscale every single service to support even the most extreme case. Are we ready for the event? Absolutely. However, it's not practical from a business perspective because it's always a fundamental trade-off between infrastructure cost and availability risk. Like this chart shows you, the more we spend on infra, the less customer impact. The less we spend, higher risk of customer impact. Simple as that. But the challenge is to find that optimal point on this curve while maintaining excellent customer experience while being fiscally efficient. So how do we do it? Our approach is simple. Measure the risk and prepare for it. We first produce probabilistic forecast instead of a single point estimate to quantify the risk we're taking. We pick 1 percentile like P90 based on the risk-cost trade-off we make. We then use stress tests for readiness assurance. We test our services not only to the expected peak traffic, but also to their breaking point. We understand unexpected things happen, so we are prepared with reactive measures to mitigate the risk. For example, we use feature tagging to reduce the compute cost for some requests. We also optimize our backup capacity pool based on the risk we are taking and use it as insurance against our unexpected situations. Here is something critical. Services are not isolated islands. They are actually connected in incredibly complex ways. Remember the bucket effect. The capacity of the system is determined by the weakest component. So all services have to work together as a network. That means we have to achieve consistent scaling across all components. What exactly does that mean in practice? We use traffic call fan-out ratio to examine the scaling level consistency. For example, if on average 1 call to service A means 2 calls to service B, we need to make sure our scaling level is aligned with that expectation on average. We understand that the fan-out ratio changes over time because of new deployment, so we have a process to monitor the fan-out ratio and update our forecast. And of course, at the end of the day, we rely on stress tests before the event for validation and identify the services that potentially run hot during the peak event. Now let's fast forward to the event itself. We understand reality rarely matches expectation perfectly. For example, more customers may show up. They may do more searches this year than last year. So we produce this mini-level traffic forecast during the event, like this chart shows you using synthetic data. The blue line is the actual traffic metric. The purple band is the forecast range. We anticipate critical moments using this forecast, like the sharp increase at event launch, like the peak hours when the traffic is at sustained high traffic volume. We focus our monitoring attention to those peak critical moments. Based on what we observed during the event, we update our forecast in real time for the rest of the event so that we can have up-to-date scaling guidance and also have enough lead time to respond. External events during those peak shopping events create unique challenges for our forecasting models because it's not really technical challenge, but behavior predictions. So let me share one interesting anecdote. Brazil and Serbia plays on November 25th, 2022 for the FIFA World Cup. The twist that makes this challenging for us is that that day was also Black Friday, the biggest shopping event in Brazil. We learned from our Brazil business team that all Brazilians will watch that game during that time, and the whole country would stop.
As someone from Brazil, I can confirm that.
So now we have two conflicting behavior drivers. One is the biggest shopping event. The other is a culture event that puts all Brazilians to the soccer game.
Yep.
So we forecast the impact with surgical precision. We anticipate sharp traffic drop during the 90-minute game and a sharp increase after the game. We proactively communicate the forecast difference with our service owners. That's exactly what happened, and no surprises during the soccer game.
Well, thank you very much. And if you want to know more Amazon's Cloud Tune Science team, you can check out this white paper. And thank you very much.
Thank you.